All right, everybody, we're gonna get started. Sorry for the delay. I'm gonna give you guys a few minutes to read the problem statement and make a copy if you aren't working on like an iPad or anything. So I'll let you have those few minutes. All right, let's get started. So from our problem statement, we were asked to find number one, the permanent set, or what it's really asking is for the strain that remains in the specimen when the load is released. And number two, the modulus of resilience before and after the load application. All right, so we have our little specimen over here. I'm just going to say it's a rod. And the material that we were given was aluminum alloy. And these arrows are just to show that there is a force happening on both sides. Okay. And we were given in our problem statement, sigma is equal to 600 megapascals. And we were given a stress strain curve graph. All right. So this big old graph is the stress strain graph. So the stress is our y-axis and our strain is the x-axis. Sorry, give me 1 sec. I'm gonna close. And just so you guys know, strain is unitless, so it can take any units that you want it to. So for this one, it's going to be millimeter over millimeter. Now, you guys have been learning stress strain graphs in class, and you know that this is loading. Oh, can y'all see that? I know it's a little, okay. Okay. So this is all loading. So there's arrows that are happening. I feel like you probably can't see those, but. So all the way from point O to about point B is loading that's happening on our rod. And then from point B to point C, we're unloading. Okay. So at point B, that's when our unload starts. And we know from class, usually our elastic region, so this whole area here, from point O to point A, that is our elastic region. So that means that our rod is taking some stress, some load, and if we take that off, it will go back to its original form. So it's not changing at all. And then from point A all the way down to point B, that is our plastic region. So we have a line going from point B to point C because our material is only stressed to 600 megapascals. So once it hits 600 megapascals, it's just going to go to that unloading phase and we're dropping back down. If we weren't stopping at 600 megapascals, we wouldn't have this line here. And F is the continuous stress that's happening on the rod. So if we didn't have the line going from B to C, from point A to point F, that would be our whole plastic region. Okay. But for right now, for this problem, we're not going to worry about what's at point F. Okay. I think that's all I want to explain on this page. So I'm going to go to a different page. Does everyone have what they need for this? Yeah, okay. All right. So like I said earlier, we were asked to find the permanent strain. Determine the permanent strain that remains in the specimen when the load is released. So like I said earlier, at point B, that's when we start unloading. Okay. And if we're asked to find permanent strain, we're asked to find epsilon. So strain is always epsilon. It's supposed to look like this, but I don't want to draw it like that. I just want to draw it like that. So let me see. Get a pen. So we have point O, point C, and point D to really worry about. So I'm going to draw this line. It's to show from point O to point D. Okay. And then we have C right here. If we were asked to find the permanent strain that remains in the specimen when the load is released, we really want to focus when the load was on our rod until it got taken off. So it was unloaded at B, and point C correlates to point B, okay? So we are really wanting to find epsilon of OC. So this is what we're trying to find, epsilon of OC. So back to my line, we know that we have 3 points, and epsilon OD, that's the full line. So that's going to be probably important for our equation. And then we have epsilon OC. So this is point O, point C. And then we also have point C and point D. I'm just doing this so you guys can see it visually a little easier instead of just looking at the graph and like trying to figure it out. So we know we have epsilon OD, we have epsilon OC, which that's what we're trying to find, and we have epsilon CD. So we know if we do some simple subtraction, if we were given, wait, sorry, one sec. Let me make sure I'm doing this right. Yes, okay. So we know epsilon OD. Okay, I was confusing myself. Epsilon OD is the whole line. If we subtract epsilon CD from it, then we'll get the remaining epsilon OC, which is what we're trying to get. So in our problem statement, they were very nice. And they already gave us the epsilon at point D, which is the total from epsilon, from point O to point D. Okay, so epsilon OD is equal to 0.023 millimeters over millimeters. So we really need to find what epsilon CD is to find what epsilon OC is. And I know you guys have learned Hooke's law. So we know Hooke's law is sigma is equal to Young's modulus, big E, times epsilon, R strain. So this is epsilon CD, and then sigma will correlate to point B. But we don't know what Young's modulus is. And Young's modulus is just the characteristic of the material. Young's modulus will never change in your problem statement. It will always stay the same, okay? So we need to find Young's modulus. Well, we can do Hooke's law. Again, sigma is equal to E epsilon. Now we need a sigma and an epsilon to find what Young's modulus is. And Young's modulus is the slope of the elastic behavior region that's going on. So that's Young's modulus there. And we know that for our elastic region, our sigma is 450 megapascals, and our epsilon for our elastic region is 0.006. So now we can find our Young's modulus. So E is equal to sigma over epsilon. So like I said, sigma is 450 megapascals, and our epsilon is 0.006. millimeters over millimeters. So we're going to get 75,000 megapascals. I'm just going to keep it in mega because we're working in mega. You can convert it to giga if you want, just your preference. So now that we have our Young's modulus, we can now find our epsilon CD. So if we bring down that and we rearrange, so we'll have epsilon CD is equal to sigma at point B equal to Young's modulus. So then our sigma at B is 600 megapascals all over 75,000 megapascals. So our epsilon CD will be 0.008 millimeters per millimeter. So now that we have our epsilon CD, we know what our epsilon OD was from our stress strain graph. We can now find our epsilon OC. So epsilon OC is equal to epsilon OD minus epsilon CD. Our epsilon OD we found to be 0.023 millimeters per millimeter minus our epsilon CD, 0.008 millimeter per millimeter. So epsilon OC will be 0.015 millimeter per millimeter. Are we all good? Any questions? No? Okay. Does everyone have it? Or do we need a minute? All right. Moving on. So for the second thing we were asked to find was the modulus of resilience before and after the loading. So I think you guys learned modulus of resilience, I think, on Monday. And modulus of resilience is represented by a UR. And modulus of resilience is usually found in the elastic region, okay? I'll explain in a minute. Okay, point B was when we started unloading. So that will be our after, okay? And from point O to point A, that will be before the loading. I know I said earlier that we're already loading from point O to point A. I think it's really asking for before the loading, before the plastic behavior starts happening, okay? Modulus of resilience is usually the area under the curve. And we can see that we were given two perfect triangles for us. Yippee us. So this will be our before the loading triangle. And then the pink will be are after the loading. All right. So if we're going to focus on before the loading, like I said, modulus of resilience is usually the symbol UR. And I said it's the area under the curve. Area of a triangle is 1/2 base times height. So 1/2 times our height, which is sigma y, times our base, which will be epsilon y. So 1/2 times sigma y, which is 450 megapascals, times epsilon y, 0.006 millimeter per millimeter. So this is 1.35 megapascals times millimeter over millimeter. So for this problem, we're not going to leave it just like this. We're actually going to convert this pascals to joules, but I'm going to show you step by step on how we're going to get there. So first, we're going to get rid of this mega. So mega is represented by 10 to the 6 pascals times millimeter over millimeter. Pascals is Newton per meter squared. And like I said, strain can take any unit you want it to. And we were given a meter down here. So I'm going to just say that this is going to convert to meter over meter. So then that will be 1.35 times 10 to the 6 Newton times a meter over meter cubed. A Newton times a meter, that is our joule that we're looking for. 1.35 times 10 to the 6 joules per meter cubed. You can keep it like this if you wanted to. I'm just going to convert the 10 to the 6 back to mega. So our final answer will be 1.35 megajoules per meter cubed. All right. So now we're going to focus for after the load. And like I said earlier, your modulus of resilience is the area under a curve. Our area under this is a triangle. So UR is equal to 1/2 times the height. So it's not going to be sigma y. It will be this 600 megapascals, okay? I'm just going to write the equation for you guys. Times our epsilon. So this will be 1/2 sigma at point B. Our epsilon will be our epsilon at CD. Epsilon at CD. All right, now we can start plugging in numbers. So 1/2 times our sigma at point B is 600 megapascals. And our epsilon at CD, we found earlier, it's 0.008 millimeter over millimeter. So then our UR will come out to, 2.4 megapascals times millimeter over millimeter. And like For the before the loading, we want to convert that to joules or megajoules, whichever one you want to use. I'm not going to write this all down again. Hopefully you can kind of see from the first one how we get to the second one. So it's just UR is equal to 2.4 megajoules per meter cubed. Is there any questions? Okay, good. That's good. Hopefully. Well, that's all I had for you guys today. Yeah. So y'all have a good weekend, okay?